Hey, so welcome back, and this is another daily code problem. So today it's called Paint House, and it's a medium level dynamic programming problem. And so basically what you're given here is just a two-dimensional array called costs. Now the number of columns here is always a fixed size, so there's always going to be 3 columns, but there can be basically n number of rows. And so what these columns represent is basically the cost of a particular paint or color of painting a house. And so essentially you can either paint the house red, blue, or green. And so each house basically, and so we basically have these rows here, right? And each row is going to represent like some particular house. So this could be like house 1, for example, or I guess it's 0 index, so house 0. This would then be house 1 and so forth, right? And then the columns within these arrays are the cost of painting them a particular color, so basically red, blue, and green. And so the first house here, to paint it red, would cost 17, the second house 2, and the third house would be 17. All right, and so essentially what we want to do is we want to paint them such that it's the minimum cost to paint all the houses. And the only constraint here that we have is just that, okay, well, you can't actually paint adjacent houses the same color. Can't really find that here. Yeah, cost, yeah. No 2 adjacent houses can be the same color. All right, and so that's what kind of makes this challenging is, okay, it's a minimization problem, and there's this constraint here, and typically when you see minimization, that kind of screams a dynamic programming problem. And so what I did, and I'm initially going to show you the top-down memoization approach, and then we'll do just the iterative kind of true dynamic programming way of doing it. But basically, at every step, say we're at house 1 here, we can have like 3 different paths. We can paint it red, we can paint it blue, or we can paint it green. And then after we've chose what color we want to paint it, we're now at house 2, right? So this is house 2, and house 2. And so then their choices are kind of minimized where they have now 2 paths. So house 2 can either be painted then, if you previously chose red, it can either be painted blue or it can be painted green. If you painted house 1 blue previously, it can be painted red or green. And as you can imagine, if you painted it green, you can either choose red or blue, and so forth. So then you would go on to house 3, and then it would be then minimized, and you can kind of imagine what comes next. Okay, and so if we want to do that top-down approach, I'll show you it, and then I'll show you a more optimal way, but it's important that you understand how to do it this way first. And so if we want to translate that recursive relationship into an actual algorithm, we first want to define our DP array, or our DP function, sorry. And this is kind of templated code that you typically write. So we want to write our recursive function. I is going to represent like which house you're currently at. And then we'll also say, okay, what was the previous color that we just used? Now, initially the previous color would just be -1 to represent we haven't painted anything previously. And we want to add our base case here. So our base case will be, okay, if we're kind of going out of range, let's just return 0, and that kind of propagates the answer back up. And so if I is greater than or equal to the length of our cost array, let's just return 0, because you don't get anything extra, or there's no extra costs for painting nothing. And then you just want to say, okay, we want to return some min cost here. And so let's go ahead and define that variable. And initially, this is kind of another templated or a common pattern, is you just set it to infinity. And so that just makes sure that we minimize it. And so then we just want to iterate. So for I, or really for every color in the range of our 3 different colors here. And so they range between like 0, 1, and 2 to represent the columns. And so for every color or column, I guess, in that range, let's go ahead and get the new minimum cost, which is just the minimum of itself. And we're going to recursively call this function, but at the next level, and we're going to set the new previous to the color that we just chose, which is C. But then to actually be adding the new cost, or the cost of the color that we're just using, let's just do plus, and then basically grab from our cost array, what am I thinking here? This particular cost of that color. All right, so let's go ahead and try running that. Oh, looks like there's something wrong. So this, yeah, sorry. So this is a two-dimensional array, so we need to specify the current level that we're at, which is I. All right, and let's go ahead and run that. Any time now? It's taking a little bit of time. Wrong answer. Let's think here. So that is I. We definitely want to return 0 on our base case. This is the range that we're operating in. And this is our min cost, which we minimize each iteration. We call our function recursively, iterate to the next level. This is the cost of the color. So we just want to make sure that one check here, that one constraint, that we're not using the previous color. So if the current color does not equal the previous color, then that should be good. Awesome. Let's go ahead and run that. Try it again. So if the current color does not equal the previous color, then we should be fine. Time would have exceeded. Let's go ahead and cache it. And success. So sorry about that, I forgot to cache it. That's just because, well, naturally you would be able to follow down multiple different paths that you've already pre-computed before. And so we just want to make sure that we cache any pre-existing work. So that's the memoization approach to this. But this runs in a worse time complexity than we could. So because the way we're doing it, it's going to run in basically 3 times O of n, or n times 3 basically, which is really just O of n, because you don't need this constant. And so that's going to be both the time and space complexity for this. But we can do better, and we can reduce it down to an O of n time complexity, but then an O of 1 space complexity. Okay, so let's go ahead and do that. So the way you can kind of convert this into more of a bottom-up approach is we're going to use this existing array and modify it. But what we're going to expect is we want to return at the end of this some minimum. And so basically we're going to propagate forward from the left to right, or from beginning to the end, the minimum answer. And this is kind of a common pattern that you would see. And as you do more problems, you'll recognize this pattern. So essentially what you're going to want to return at the end of this is the minimum of the 3 possible paths that you could choose at the very last house. So the last house is basically going to contain the minimum cost to paint that house a particular color for all the previous houses as well. And so we just want to have the minimum of those 3 different possible paths once we've aggregated it at the end here. And so in order to do that, all that we want to do is we want to iterate through all of the houses here. So I should say for I in the range of, well, the length of the houses, or the length of the cost, or really the number of houses. So, and essentially we just want for every iteration to be kind of computing the new minimum cost at this particular house. And so it's going to start from 1 onwards, and basically it's just another common pattern where you just start at the next house and look backwards. And so we just say, okay, the cost at this particular house, and we're basically going to repeat this 3 times here. So the cost at this house with this color is going to be equal to essentially just the minimum of the cost of the previous house at the other colors. So that's going to be basically color 1 as well as color 2 because we're using 0. And let's go ahead and we're just going to repeat this 3 times, and I'll just further explain this in a second in case you have any other questions. So let's replace, oh, this was 0. And then this one, you can choose 1 because you're using 2. And this one, yeah, you want to use 2 because you're using 1. Let's go ahead and run that. Oh, we have a problem here. What could that be? So, we're not actually aggregating that answer as we move along here. And so what that's going to be is we want to add that as we move along here. There we go. So let's go ahead and run that. And there, it would be a much better time complexity because we're using, or much better space complexity because we're using all of one space, but it would be the same time complexity. But so essentially, once again, what we're doing here is as we move from left to right, we're going to be starting with basically, once again, we have rows of houses, and we're always going to be looking at the current house and the previous house here. And we're basically saying, okay, at this current house that we're at, with 3 different paths, let's look at what's the cost of adding this color plus the aggregated kind of running sum of what was costed here. And so then we take the minimum of those 2 other possible paths and place it here, and this kind of gets updated, right? And so then we update this one by looking at these 2 possible paths, and same thing here. And the way this kind of aggregates forward is then when you get to the next row, this aggregation that we just did of the previous row can then be aggregated here by this color, considering these 2, which once again, these have the aggregated cost of not only this row, but also this row. And so then it gets aggregated forward and so forth. And so once you kind of reach the final house here, it'll have 3 possible paths of the red, blue, and green with the aggregated cost. And so you just want to choose the minimum of these 3 kind of possible paths. But yeah, I hope this helped a little bit, and good luck with the rest of your algorithms. Thanks for watching.